Hello everyone, my name is Roman Pelopet. I am currently in my first year as a PhD student. Today I am going to present our research on analysis of mean square estimator errors of basic frequency for periodically non-stationary random processes. This work has been conducted in collaboration with Igor Yavorsky, Roman Yuzefovich, Roman Slipko, Oleg Lechak, and Pavlo Semenov. Periodically non-stationary random processes (PNRPs) are the stochastic models of hidden periodicities. Such models can be applied to describe the irregularity and recurrence of time series, which explains different nature of processes. When representing a PNRP in the form of series, that is defined by equation 1. The moment function of the processes determines the periodic changes in the mean and covariant functions, which can be represented in the form of Fourier series in a following way. The Fourier coefficients of the series in equation 2 and equation 3 are defined by modulating processes and expressed as in equation 4. Discovering the hidden periodicities using this model of signal as a PNRP has been considered in a number of works. The statistical properties of the estimator of the non-stationarity period were not analyzed in this investigation, but were briefly characterized. As shown, the biases and the variances of the LS estimators for the mean and covariant functions and the component estimator formed on the basis of their cyclic statistics quickly converge as the realization length draws. It was proved that the LS estimation of the basic frequency for the PNRP mean function can be reduced to finding the maximum point of the following squared functional. We substitute into the functional in equation 5 the component estimator for the mean function rather than its LS estimator. From the time averaging of equation 5, we have equation 9. Terms that depend on the function vanish as t increases. They are higher order smallness in comparison to first two terms in equation 9. So we have equation 10. Let us consider the properties of the maximum point of the functional in equation 10. This point can be found as a solution to the following nonlinear equation. When to introduce in equation 10 the normalized deterministic and fluctuation parts as follows and denote, we can decompose the left-hand side of the equation 11 into Taylor series in the neighborhood of the point omega equal omega 0. Then for the first approximation, we will have equation 12, equation 13, and equation 13. Now, if r of t and tau tends to 0 for all t in the interval of 0 and p as tau increases, the omega value that produces the maximum of the functional in equation 10 for a Gaussian PNRP is an asymptotically unbiased and consistent estimator for the basic frequency of the mean function and to a first approximation. Its bias and variance are defined by formulae. It was shown that LS estimation of the basic frequency for mean and covariant functions of the PNRP can be reduced to searching for the maximum points of the simplified functional, which are defined by the sums of the powers of the harmonics of the test frequency and its multiples. The values of the maximum points of functional are close to the time average powers of the time changes of related moment function. It was proved that the estimator obtained with such functional for a Gaussian BNRP is asymptotically unbiased and consistent if the variance function tends to zero, with time lag increasing. Formally, for the estimator variances were derived to a first approximation. Thank you for your attention.